Hello, welcome to this video. So, I'm sure you're all familiar with the Fibonacci sequence, which says that if you start 1, 1, then you begin with 1, 1, and then each number is the sum of the previous two numbers. So 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, then 13, 21, and so on. This is the Fibonacci sequence, and there is also a famous formula for the Fibonacci sequence. And you can also say that we can define the Fibonacci sequence with recursion. An plus 1 is an plus an minus 1. A1 is equal to 1, and A2 is equal to 1. So here it says the first two numbers are 1, and then this says each number is the sum of the previous two numbers. Here, and there's of course the famous formula for it, which is, if I remember correctly, phi of n minus negative 1 over phi to the n over square root of 5, where phi is the golden ratio. And we're going to use, and as a famous formula for the Fibonacci sequence, and what we're going to do is find a formula for even more generalized sequence. You start with small a, small b, and then each number is big A times the previous one plus big B times the previous of the previous one. So in this case, we'll have big A and big B, small a and small b are all equal to 1. And that's the Fibonacci sequence. H1 may be the Lucas numbers. You'll just have to change A1 to small a to 2 instead of 1. And you can get all sorts of sequences with this recursion formula. And we're going to find a nice, simple answer to it, just like the formula for the nth term in the Fibonacci sequence. We're going to find the nth term in this sequence. So, let's erase this. Okay, let's begin. So, first thing I'm going to do is a little trick to make this equation a bit simpler to work with. So, what we're going to do is erase some number k times an from both sides, and we'll soon see what property we want k to have. So we'll get an plus 1 minus kan is equal to a minus k an plus b an minus 1. So, and what I want to do is to make it so I can take, say, a minus k out of this sum, and I'll be left with an minus k an minus 1. Just like, so basically this, but instead of n, I have n minus 1. And you'll soon see why I want that. But let's first of all see what property k has to have for this to be the case. So we're able to actually do that. So we need to have the ratio a minus k divided by 1 is equal to b divided by minus k. So I'll let you think about why we want why we need a minus k divided by 1 to equal b divided by negative k for us to be able to do that, but let's write the equation down. And then we'll get from here, after a bit of simplifying, k squared minus ka minus b is equal to 0. Now, notice a, b, big A, big B, small b, all of these could be real, complex, whatever. I don't really care. But, however, even if these are real numbers, and this is, k doesn't have a solution in real numbers, we know it always has a solution in complex numbers. And if it has a solution in complex numbers, we know there exists such a k that we'll be able to do what we want to do, meaning that it is valid for us to actually do minus kan, and k has this property. Now that we know k holds this property, let's put it this. Now, I'll take a minus k out of this. So, an plus 1 minus kan. I'll take a minus k out to get an minus k, an minus 1. Now, let's call this bn. So this is bn. Now notice, if this is bn, this thing right here in the brackets is bn minus 1. So this is a minus k, bn minus 1. But if you have a series where each number is the same multiple, so you're multiplying by the same number to get the next number, bn is some constant times bn minus 1. Bn is a geometric series. And we know the formula for a geometric series is going to be that the number that you're multiplying by to the power of n minus 1 multiplied by the first number in your sequence, b1. But now notice, notice that b1 is just a2 minus ka1, which is b minus ak. Because we know small a and small b. So this is a minus k, so then minus 1 times a minus ak. Alright. Now this is bn, but remember, we defined bn to be n plus 1 minus kan. But how do we continue from here? Well, very simply. It's going to be actually very simple. So now, let's see. Let's look at an. From this, we know an is going to be, I'm just going to write b n minus 1 plus k an minus 1. But then we know an minus 1 is bn minus 2 plus an minus 2. And if we take it out of brackets, we'll get bn minus 1 plus k bn minus 2 plus k squared an minus 2. And then if we continue on like this, we'll get that eventually, after replacing each number with this formula of bn, until we get to a1, we will find that the sum going from 1 to n minus 1 of bi times k to the n minus 1 minus I plus k to the n minus 1 times a1, which is just small a. And it might seem a bit think about it for a second, and this is the result that you should understand why this is the result we should get. And the formal way to prove that this is the case is with induction. I won't do it here because it's just a bit tedious, but you can do it yourself at home, and you'll find that it's pretty easy to prove with induction that an is just this thing. And so now we can just plug in bi because we know the formula for bn. Okay, so now we will plug in bi into here, and we'll get, this is the sum as I goes from 1 to n minus 1 of, now, a minus k to the I minus 1 times b minus ak times k to the n minus 1 minus I. This, all of this, so put in brackets so we don't confuse, and plus k to the n minus 1 a. Alright. Now this is what we have. It's just going to be taking some constants out. So sum as I goes from 1 to n minus 1 of b minus ak times k to the n minus 2 times 1 over k to the I minus 1 times a minus k to the I minus 1, doing a sum on all of this, plus k to the n minus 1, a. Now, we'll take the constants out and put these together, and we'll get b minus ak times k to the n minus 2 times the sum as I goes from 1 to n minus 2 of a minus k over k to the I minus 1 plus k to the n minus 1 times a. Okay, now, before I'll go any further and actually use the formula for the sum of a geometric series, I'll replace a minus k with b over negative k, or negative b over k, because we know it's just true from this formula, because from the property that we want k to hold. Okay, let's continue. So now we know this is the sum of a geometric series. From that formula, we'll be able to say that, okay, the first term in the sequence of this geometric series, negative b over k squared to the I minus 1, when you plug in I is equal to 1, you'll get negative b over k squared to the 0, which is 1. So the first term is 1, so we can just not multiply. So we just, and it's neutral to multiplication, so we'll just, so we won't write it down. Now it's 1 minus negative b over k squared to the n minus 2 divided by 1 minus b over k squared, so plus b over k squared plus k to the n minus 1. Okay. Now, this is technically the formula. We could really call it here, but I want something more. So, what I will do is, So what I want to do is look at, we can simplify this to get k to the n times something plus negative b over k, or k squared or something like that to the n, times another something. And that's what I want to do. So we can separate this to get b minus ak times 1 over 1 plus b over k squared. So, write k squared over k squared plus b. And then here, k to the n minus 1 times a is like k to the n times a over k. So this is plus a over k. Now, this is times k to the n. This is times k to the n minus 2. So to make it k to the n, I'll multiply it by k squared. So you can select k squared moves up here. Multiply by k to the n minus 2. It's k to the n. So this is the coefficients of k to the n. And the coefficient of negative b over k squared is b minus ak times, I'll put it down, I'll actually put down a minus because there's a minus here. So minus b minus ak times times 1 over 1 plus b over k squared. So we're divided by 1 over 1 plus b over k squared times negative b over k squared n minus 2. But then we're multiplying by k to the n minus 2, remember. And then because this is also to the power of n minus 2, we can just say k times negative b over k squared all to the power of n minus 2, meaning that this square just disappears. So these are two coefficients for k to the n, negative b over k to the n minus 2. Now I'll multiply top and bottom by negative b over k, by b squared over k squared, just to make this a power of n. So this minus 2 disappears, and so I'll multiply here by b squared over k. K squared. And now this should be it. But let's now here comes the stuff that is a bit tricky to understand. So k is the root of k squared minus k big. It's the root of k squared minus k big A minus b, and it's a solution to this equation. But notice from the Vienna formulas for roots of polynomials, the second solution to this equation is negative b, which is this, the free coefficients over k, because k times that number will be negative b. And so we actually get that this is the first root, this is the second root. And we chose k to be one of those roots. But we chose k to be one of those roots. But we, at the same time, could have chosen the other root of this polynomial, or the second solution to this equation, and we would have gotten the same thing. K would have instead been negative b over k, and we would have gotten the same thing. And what I'm trying to say here, if we replace k here with negative b over k, we should exactly get this. Now, and so if I simplify one of these, then I will get, then I'll just have to replace k with negative b over k to get the second one. So let's actually not simplify this, let's simplify this. So, and now, instead of negative b over k and k, I'll write k as k1, the first root, and the first solution, and negative b over k as k2, the second solution. So I'll get b minus ak1 divided by 1 plus k2 squared, no wait, times k2, 1 minus k2 over k1 times k2 squared. Okay, now we'll get, this is bk1 minus ak1 squared all over this is over k1 minus k2 times k2 squared. And that's going to be the coefficient. So this is going to be, I'll just write it as C2 for short. And C1 will just be when I replace K1 with K2 and K2 with K1. So BK2 minus AK2 squared over K2 minus K1. K1 squared is the first coefficients, which is this. And now I have these, and I know that AN is K1 to the n C1 plus K2 to the n C2. And if you want to check it, I'll let you check by letting big A, big B, small a, small b, all be 1, and C, if you get, and you should get, the equation for the Fibonacci sequence. But finally, this is our answer. And that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it. Plus k to the n minus 1, a. Okay, now we're getting a bit short on space here, and so let's just clear the board and write this up top and continue from there.